So thanks for coming to Gwendolyn Getliff's, soon-to-be Dr. Gwendolyn Getliff's thesis defense. Gwendolyn is a woman on a mission. She at first came aware of you when you arrived in my office and said, "You need to work with me." We won't tell the rest of that story. Good, okay. And I was convinced right there, so did a master's together, did a PhD, and then you've actually corralled all the chief technologists at NASA from all the centers.
Tell them I'll be updating.
I think for my good, but I'm not sure. But also ran a major program called the NIAC program here at MIT, and did a spectacular job with our collaborators at various locations around the country. So,
well, thank you for that glowing introduction. So,
expecting worse.
I don't know what I was expecting. So good morning, everyone. Thank you for joining us this early on a Friday. I'll be talking to you today about magnetically enabled structures using interacting coils, or MAJESTIC for short. And MAJESTIC was a 3-year program under the NASA Innovative Advanced Concepts Program, or NIAC. And it was focused on developing the concept of electromagnetically supported space structures. So I'll discuss that in general, but the greater focus of this talk is on the stability of such structures, and that's a greater emphasis on my thesis as well. Next slide. So I'm going to start with a little bit of background and motivation for why we're looking at electromagnetically supported structures, talk about some previous and existing work in the field, and then go through some of the objectives of this work. Next slide. So first, before we get into it, I want to give you a little bit of a refresher on electromagnetic forces from your Physics 1 class, however many decades ago. Current carrying wires produce a magnetic field, and when current carrying wires are placed in an external magnetic field, such as that created by another current carrying coil, experiences forces and torques. And so we're using coils here instead of straight wires throughout this work. And so whenever a moving set of charges interacts with the magnetic field, those forces are caused. And so basically the magnetic field, you can derive the forces at each point around a coil, sum them together to get the net force, or use them to derive the torques around the center of the coil. And so you may have played with bar magnets or permanent magnets more than you've played with electromagnets. So when I talk about repelling coils with currents running in opposite directions, it's very similar to 2 bar magnets with like poles facing each other that are forcing each other apart. And you'll know from experience that any sort of deviation from directly aligned and repelling will result in forces and torques that swing the magnets around such that the dissimilar poles are contacting. And so all these formulations and tendencies are applicable to both regular conductors and superconductors, but we assume the use of high temperature superconductors throughout this work because they are capable of higher critical current densities, and so that extends sort of the range of and length of structures that we can consider in work. And so high temperature superconductors are those that are superconducting below a critical temperature that can be achieved using liquid nitrogen as the coolant. And liquid nitrogen's boiling point is 77 Kelvin, to give you some scale. Next slide. So the general motivation of this technology is to enhance existing missions and enable ones that were not previously possible. And so in general, larger spacecraft give you better performance. We use the example of a telescope a lot. So a larger primary telescope mirror gives you greater light collecting area, finer angular resolution. But the size of your spacecraft is greatly constrained by your launch vehicle dimensions and by the exorbitant cost for you to mass to launch something. So in general, we want a lightweight, large system with a high stowed to deployed ratio. So one of the main objectives of spacecraft design is to make the system as light as possible. And so the structure, because it's sort of a dumb subsystem, it exists to position other things with respect to each other. It's a target of mass production often because the structure represents 20 to 30% of the spacecraft dry mass. And so there's a couple of different ways you can think about reducing the mass of a structure. If this is a notional diagram of your total mass of your system, and here's your structure at like 20 to 30%, you can try and reduce the parts. You can try and make a lighter structure, like with isogrid panels, trying to hollow them out and make the structure as low density as possible. You can try and reduce the sum of the parts by having this structural subsystem fulfill these other functions that are generally attributed to other subsystems. And I'll talk about these ancillary functions in a moment. Or you can try and do both. You can try and make it a lighter weight structure that also fulfills and saves size, weight, and power from these other subsystems. And so electromagnets are capable of structural and other functions. And so they are, this is the major reason that we're studying electromagnets for the structural purposes. So some of these ancillary capabilities, and I've italicized the ones that can be performed with superconductors in particular. Some of them are, for instance, contactless controllable actuation of spacecraft with respect to each other, which is a major reason why we're considering this for making lighter weight structures, because you have sort of instances of mass, but then very little mass in between them. Lossless energy storage is another thing you can do with superconductors. Low exported vibration heat transfer, because you have so little or no connected hardware between the elements. Wireless power and data transfer. So one way you can visualize a lot of these ancillary capabilities is, next slide, with this conceptual notional image of a next generation space telescope. And you'll see it bears a striking resemblance to the James Webb Space Telescope, except instead of having a rigid hardware connecting, for instance, the bus, the sun shield, and the cryogenic primary and secondary mirror assemblies, they're free-flying with respect to each other and using electromagnetic forces to position and orient them. And so this is, ideally you wouldn't be doing all of these things on the same spacecraft, but it's a good way of sort of depicting some of the potentials. So for instance, wireless power data transfer between the elements. I mentioned electromagnetic formation, flight, and positioning of those spacecraft parts with respect to each other. The potential for momentum trading between the elements. Since you're able to move them with respect to each other, you could, for instance, reduce a center of pressure, center of mass offset that requires desaturation of your reaction wheels over the course of perhaps a halo orbit around the Earth's L2 point, as in James Webb. A couple of the advantages you get from these functions is that you don't have obscuration of the primary mirror from the secondary mirror from like attaching an attachment tower. You could potentially stage the deployment, not have to fit the whole spacecraft into one launch vehicle, but deploy these at different times and maybe replace elements of the spacecraft rather than the entire thing. Expansion from a stowed position, the superconductors that line, for instance, the sun shield, act to tension the spacecraft as well as splay the layers apart. So you actually get that separation, that tensioning without needing, for instance, long masts that are pulling and cranking and winching. I mentioned dynamic and thermal isolation, the concept of maybe a membrane mirror with low mass due to the lack of a backplane. Next slide. So there's been a lot of previous work on these elements, and the scope of this thesis and of Majestic in general is really focused on that expansion from stowed within the launch vehicle, the stiffening and tensioning of spacecraft elements with respect to each other. And so probably the closest thing to what we're proposing was proposed by Powell in a previous NIAC study, and it's magnetically inflated cable structures. And so he was really imagining these kilometer-wide and long telescopes and, for instance, deployed radiation protection systems. And so it was really visualizing the ability of a flexible coil to expand and tension itself. And so we really sort of took those qualitative ideas and built on them to really quantify them and what we could do with them. So next slide. So I keep mentioning these structural functions. And so they involve one or more coils interacting or connected with each other. You can see that there's basically 4 that fall in the deployment regime, and then 3 that sort of are variants of those that occur later in the spacecraft life cycle. And so, for instance, I mentioned the tendency of a flexible coil to expand. Inflate, unfold, and separate are all functions that involve rigid coils that are attached by some sort of elastic hardware, like a hinge or a mesh or tethers of some sort. And so 2 of the 4 main risks that we determined in the Majestic study that have to do with electromagnets and deployment were initial instability of the configuration at spacecraft commissioning, and operational disturbances over the course of the spacecraft lifetime that could potentially perturb it and result in instability, including solar pressure, cryocooler vibration, the Earth's external magnetic field that exerts torques on any coils that you're going to put in it. So our goal was to reduce these risks in particular by studying the stability of such structures. And so this work focuses, we picked sort of a separate configuration as the example case, and so we're looking at the stability of a mast that's supported by these tethered repelling coils. Next slide. So this slide shows how my work fits into the larger context of electromagnet stability and spacecraft stability. So I'm right here, sort of spanning this space. This bigger bubble is basically spacecraft stabilizing, attitude control, and positioning techniques that you can use. As a subset, I have passive stability. In my thesis, I refer to it as pseudo-passive stability because it refers to techniques that do not require active control, but they do not necessarily represent a lack of energy being required. And sometimes passivity is defined as techniques that require no consumption of energy. And obviously, in the case of electromagnets, you are putting energy into the system in order to achieve this stability. And as a subset of that, I have large spacecraft, and these are those techniques that require certain lengths and geometries in order to exploit. And so my work sort of falls into that bubble because it does require certain distances and geometries, but it's also scalable to smaller distances or larger distances, and so it sort of spans that space. In the general space of electromagnet stability, you can see that a lot of these sort of cross between superconducting and electromagnet stability because you can do it multiple ways. For instance, this platform over here uses permanent magnets to sort of hover, but you can also do that with bulk superconductors and that kind of thing. So some of these techniques can be done using either superconductors or electromagnets. And the main thing that I'm building on in this work is Frank Moon's at Cornell's work in superconducting levitation and magnetosolid dynamics and mechanics. And so he defines the term magnetoelastic structures, and he uses that to refer to structures that deform elastically under magnetic effects. He generally uses that to refer to material deformation, but we're using it to refer to rigid bodies with elastic hardware that is deforming under magnetic effects. And so he sort of introduces the concepts of magnetic stiffness and some of the combinations of magnetic and elastic effects. And so his work is sort of a progression of some of those concepts that he put forward. I have Jackson's classical electrodynamics down here because though it doesn't specifically focus on stability, it has a lot of the fundamentals and laws that I use in order to actually do the work. So next slide. So from this, we're presented with sort of three main research questions. And the first one I don't talk about a lot in this talk, but it's in the thesis. And it's what applications would be enhanced or enabled by electromagnetic subsystem. And so that's sort of the chapter 2 of my thesis. But the ones I'm going to focus on today are the second two, which is it possible for 2 or more connected electromagnetic coils in space to be passively stable? And if it is possible, then what are the conditions on the design and the operation of that system such that it achieves stability and maintains it? And so from this, we can see that we need a methodology, a validated methodology that we can trust for determining the stability of such structures, as well as the sensitivity of that stability to design parameters and imparted energy and perturbations over the system lifetime. And so the goals of the methodology, which we'll come back and see if we've met later, are that it's useful, scalable, and that it's also plausible. So this is something that actually has applicability to real-world structures. Next slide. So now I'm going to give you some definitions of stability. I keep tossing that word around. What does it mean? Tell you about the approach that I took in the thesis, as well as the steps I used to validate it, and then introduce the models, the system models that I'm using in the next section, which will be sort of the results. Next slide. So we'll start with equilibrium. Equilibrium occurs in a system when all the forces and all the torques sum to 0 in all generalized coordinates of motion. And this also corresponds to when the partial derivative of potential energy with respect to those coordinates is 0. So if you look at this diagram to the left in orange, it shows, for instance, 1 degree of freedom in x and the potential energy curve as a result of that. And so the equilibrium conditions are met at each of the peaks, valleys, and plateaus in the structure. There's an equilibrium. And so the stability of those equilibria is then determined by the second derivative of potential energy with respect to that degree of freedom. And so that's also analogous to the stiffness of the system. The stiffness is the derivative of force or torque with respect to those directions. And so you can see that they're equivalent conditions. And so stable equilibria require that the second derivative of potential energy is positive in all directions. If you have instability in any direction, it's an unstable equilibrium. And that refers to saddle points, for instance, where it may look stable and like it's at the bottom of the well from one direction, but not in the other. So you can see that stable equilibria are those that when you perturb them slightly, tend to return back towards the initial equilibrium. Unstable equilibria, which are those that have any of these second derivatives being negative, tend to diverge away from equilibrium when perturbed and go towards a direction of lower potential energy. And neutrally stable are those that when you shift them slightly, they tend to stay in place and not move in any direction. And that's when the second derivatives are roughly equal to 0. And so once we've found at least one statically stable equilibrium, we can then evaluate the dynamic stability of that statically stable equilibrium. And so for instance, this is a replotting of this orange plot, except we've labeled the equilibrium with letters A, B, C, and D. Point B is the one that we're focusing on here. And so the energy at that stable equilibrium is P sub EQ. The closest unstable equilibrium in terms of how much energy it would take to reach it is point C here. The energy there is P sub C. And so you can imagine if you start with no kinetic energy in the system and your energy is equivalent to PEQ, you're just going to stay at rest there. If you start with some initial kinetic energy or with a higher potential energy than P sub EQ, you're going to have bounded motion around that equilibrium point. In this case, if you start with an E sub T naught, your motion is bound between x sub 1 and x sub 2. And you can see that if you start with an energy at or above P sub C, your motion is going to be unbounded and you're going to diverge from that equilibrium. And so we refer to the difference between the potential energy of the closest, basically the minimum statically stable equilibrium surrounding the point, and the energy at equilibrium. We call that the critical initial kinetic energy. And that's the kinetic energy you have to start with or have added to your system at some point, that for a statically stable equilibrium to become dynamically unstable. So as long as the energy in your system is below that critical initial kinetic energy for that point, you'll have bounded motion and be dynamically stable. Next slide. So I mentioned I'm going to go through the approach. And so the philosophy of this approach is to begin with a very simple problem that we can really conceptually and intuitively understand. And then go from there and add complexity and nonlinearity while validating each step wherever we can, so that when we get to these more advanced problems with less intuitive results, with fewer closed form solutions, we have confidence that our methodology is still applicable and still giving us the same conditions on stability. The process here, I mentioned equilibrium, static, and dynamic stability. We find each of those, and so we find the forces and torques balance. We examine the stiffness of the system. Positive stiffness represents static stability. And so we can identify which of those equilibria are statically stable or unstable. Then, for the statically stable points, we can calculate that critical initial kinetic energy by calculating the potential energy curve, either as a direct integration of a nice analytical integrable formula, or, and I'll get into this later, use the vector potential in order to calculate the energy of the system, and then do that differential to find how much needs to be added. And so we do each of these three steps for each of three successively more advanced and complex problems. And so they represent chapters 3, 4, and 5 in my thesis. And so they're numbered as such. And so the analytical solution starts with modeling the coils as point dipoles with nice closed form solutions for them. We calculate static and dynamic stability directly by differentiating or integrating them. Then we go into sort of what's more of a validation chapter in chapter 4, where we have the same simple system model, but we're using numerical methods to verify that we're getting the same results as the exact solutions. And then in the complex case, we're using a whole new model, but we're using those same numerical methods that we've validated. Next slide. So I mentioned validation. So each of those steps, the results of them, are used to validate a number of things. For instance, in the analytical case, it's the numerical methods that will be used later, as well as the vector potential approach. For the simple numerical case, it's validating that the coil model and the dipole model are giving similar things. It's validating that the two different coil models give the same thing. It's validating the vector potential approach is still valid when you're using this kind of model versus the dipole model. And it provides confidence in our findings so that we can, after we've gotten to this final step, then apply it to real-world systems or things that more closely approximate what a spacecraft designer would actually be trying to design. Next slide. So I mentioned I would go through some of the system models. There's two main models that are used in this thesis. One is the dipole model, which is used in chapters 3 and 4. It takes two different magnets and it models them as magnetic dipole moments pointed in the direction of the North Pole in these diagrams. And again, I mentioned they have closed form analytical solutions. But the reason you can't use these for the system all the way throughout is that they overestimate the field strength as they get closer together. So when I say near field, I mean when the coils are at distances apart that are less than roughly 10 coil radii. At 10 coil radii, you have about a 5% error in that field strength. And as they get closer, that error increases. And so we don't want to use this when we're modeling magnetic coils because they don't really approximate coils well in the entire span of the design space. So for chapter 5, we move to modeling them actually as current carrying loops. We assume constant currents in this case for most of the work. And then there's a more complicated formulation for the force and torque that's not as neatly expressed, that's based on discretizing the coils and calculating the contributions from each element along them. But it is more accurate. It can be used for as close together as you want or as far apart as you want. And so in each case, we have two magnets. We fix the left magnet at the origin. It's not allowed to translate or rotate in any way. The second coil is attached with a linear spring along the x-axis with spring constant K, and a torsional spring that prevents rotation around the z-axis. And so the angle of rotation around z is beta. So you'll see me use x and beta to refer to those degrees of freedom. And that applies for both coils. And so within each of these cases, we look at a 1 degree freedom translation system where coil 2 is allowed to translate in x, but only x. A 1 degree of freedom rotation where it's fixed in x and allowed to rotate around z. And then the combination of the two where it can both translate and rotate. And so this explores sort of a couple of the different modes of instability that you might see in such a structure and allows us to compare between the models and see sort of what's going on and where certain features of the plots and results are coming from. Next slide. So now I'm going to go through sort of the results of each of those chapters 3, 4, and 5. And this is a simplified version of that approach matrix. I'm going to put in the upper right-hand corner so you can sort of remember and see where you're centered in the analytical, simple, numerical, and complex numerical case, just to sort of guide you throughout the rest of this talk. Next slide. So we're going to jump right in. We're going to start with the chapter 3, the analytical case, where we have the two magnets modeled as dipole moments. And the right one is allowed to translate. So we go through each of the steps: equilibrium identification, static stability, which has sort of an internal validation against another approach for determining the stability of a system using the state space formulation and comparing eigenvalues. And then the dynamic stability by calculating the potential energy. So the plot on the left, we have the distance between the coils, x, along the x-axis. We have the absolute value of force along the y-axis. And we have positive values colored in black and negative values colored in gray. So what that means is we have a single curve here that represents the magnetic force between the coils. If you look at the formulation, that magnetic force is positive because they're repelling, so it's positive in the x direction. And at this point, we see that we're starting x at 2. 2 is assumed to be the natural length of the spring, where it's not compressed or stretched at all. So when x is greater than 2, the spring is stretched, and therefore the spring force is negative. So you can see that equilibria, that force balance occurs at each place that the dipole force, which is along here, crosses. And these 6 lines represent 6 different spring constants for that linear spring. So for a very stiff spring, this curve right here, you see the equilibrium, where the forces and the elastic and magnetic forces are balanced. It's very close to the natural length of the spring. There's not much stretching that happens. As you go to progressively weaker springs, the spring stretches more. So you see this is roughly 3.2, and so the spring is stretched a fair amount. And so they're all statically stable, and you can tell that by looking at the analytical derivative, which shows all positive, all of those variables are positive all the time. So it's always statically stable in repulsion. And then this plot over here shows the potential energy curves. So again, we're looking at first distance here from 0 to 5, and potential energy to absolute value along the y-axis. And so again, black represent positive values, gray represents the absolute value of negative values. And so each of these equilibria 1, 2, 3 through 6 are shown here. And we can see from this plot that though they're all at peaks in the gray lines, those are negative values, and therefore all of these occur at the minimum value in their potential energy curve. And so they are all dynamically stable, because they all occur in those wells in the potential energy, and these are all plotted by directly integrating the force. And more than just being dynamically stable, they're globally stable because the potential energy goes to infinity as x goes to 0 and x goes to infinity. So there's no amount of energy you can add to the system to make this system go dynamically unstable and basically have unbounded motion around that equilibrium. So this is a very simple system. Next slide. So once we get into rotation, we have some more interesting results. And so again, we have on this side, we have where we're identifying equilibria. We have beta again on the x-axis, beta equals 0 here. So in this case, the coils are aligned, and as beta twists in the positive direction or in the negative direction, you're seeing that rotation. On the y-axis, we have the absolute value of torque. And again, we're using black for positive values and gray for the absolute value of negative values. And so we have 5 plots plotted here. We have the magnetic torque for each of 2 distances apart. So in this case, remember, it's fixed at a certain distance in x and allowed to rotate. So the solid line is when they're closer together at 1.75 meters. The dotted line is when they're farther apart. Those are these lines right here. And each of the lines with symbols represents a different torsional spring constant. So this one is the weakest one here. You can see it exerts the lowest amount of torque up to the highest amount here. And so again, anywhere that the black and gray lines cross represents an equilibrium. And we also see that because the spring and magnetic torques are 0 when beta equals 0, we see 6 equilibria at the origin. And it's sort of hard to tell from this plot like what the stability of those equilibria are. So we go forward and we examine our potential energy curves. And so in this case, we're plotting a curve for each combination of x naught and kr, k sub r being the torsional spring constant. And so we see that when x naught is 1.75 meters, when they're closer together, we see that all three of the curves are unstable at beta equals 0 because they're all at a hill in the potential energy. Whereas the case where we have a stronger spring constant is actually, it has, sorry, how do I phrase that? It has secondary equilibria on either side that are statically unstable. And so those occur because at the origin, the magnetic torque dominates, but then it reaches some rotation amount where the elastic torque actually meets it because the spring is relatively strong. And so you have sort of these side places where the magnetic and elastic torque are balancing, and even as you increase, the spring pulls it back. If you decrease, the magnet forces it out. So those are statically stable. And then when they're farther apart, you actually see one central equilibrium that's dynamically stable and unstable, and again, another one where you have those secondary equilibria. But this is a lot of combinations of variables to plot. It's not the most effective way to be presenting this data. So what do we do? Next slide. We non-dimensionalize. So we want to reduce the dimensionality of the variable space. We have currents, we have number of turns, we have radii, we have like spring constants. We have a lot of variables, and we want to reduce them. So we do that by scaling, in this case, all of the length terms, mass terms, and time terms by characteristic length, mass, and time values. And we pick the radius of coil 1, the mass of coil 2, and a time constant that's based on the natural frequency of the second magnet on that linear spring. And so you can see that we divide all of those terms out by their characteristic values. We use tilde to represent a non-dimensional value, except with the k case where we use stars. And you can see that if you write the equations of motion with these new terms, you can group a lot of these variables into single values. So gamma includes not only currents and numbers of turns and radii, it also includes the spring constant. So you can see that for a large gamma, you either have a very strong magnet or a very weak spring, and vice versa. And then k star, incidentally, with our choice of characteristic time value, ends up equaling 1. So in this case, we leave it in for generality, but in general, you can just look at gamma to determine what I mean, you only need one term to basically define this whole system. So you can write the force and torque non-dimensionally, and you can see that there are a lot simpler equations. So in this case, it shows the non-dimensional potential energy for the previous system we were studying, 1 degree of freedom rotation. And you can see that as gamma goes from 35 to 30 to 25, that central equilibrium goes from pretty highly statically unstable to the point where if you added another curve, you would see that it looks that it's actually statically stable at that point. And you can describe the system using one variable instead of all these combinations. Next slide. So now we'll look at the 2 degree of freedom case where we combine both the 1 degree of freedom translation and rotation. Now you're not just solving an equation, you're solving a system of equations. Stiffness is now a matrix, not just a scalar. So instead of just looking at the sign of the scalar stiffness, you're looking at the sign of the eigenvalues of that stiffness matrix. And so the magnetic potential energy can be calculated either from the force or the torque. So you see that if you integrate the force with respect to x and the torque with respect to beta, you end up getting the same functional for the potential energy, which is pretty cool. And so when I talk about effective potential energy, it's a combination of the magnetic and elastic potential energies, and we're looking for minima in that space. And so this example, this shows beta along the x-axis, distance along this axis, and then it shows the potential energy contour. So blue represents lower values, red represents greater values. So you can see that in the case where gamma equals 10, that it's clearly at the bottom of a potential energy well, and within the range that we're studying, we don't see any secondary equilibria. So you'd see that as you get to larger gamma, which is either a stronger magnet or a weaker spring, that potential energy well sort of shortens, and you see these secondary equilibria at saddle points come up, which represents, if you rotate that far, then suddenly your magnet is actually dominating your spring and you go statically unstable. So when you calculate your critical initial kinetic energy, you'd be looking at the difference between the potential energy at the stable point and the potential energy at the unstable point to find out how much energy you'd have to add at a minimum for in a certain direction of motion to get unbounded motion. And so when you get a strong enough magnet, the magnet always dominates the springs no matter what. So any divergence away from beta equals 0 represents you falling off or rotating around to try and get into that lower potential energy state. So this is an unstable equilibrium at beta equals 0. Next slide. So I mentioned that chapter 4, the simple numerical case, is more of a validation chapter. It basically uses numerical methods like interpolation between 2 points to find where the zero crossing is, as well as the center finite difference approach for approximating the stiffness or the derivative of force or torque at that crossing. And then also, and I'll talk about this more on the next slide, introduces the vector potential approach and shows that it's equivalent to the analytical potential energy for the dipole system. Next slide. So when I talk about the dipole vector potential, Gauss's law for magnetism says that the divergence of a magnetic field is 0. And that's it can be conceptualized by imagining a closed surface. It says that the net flux for a closed surface has to be 0. And because this is true for the magnetic field B is the curl of a vector field A, which we call a vector potential, magnetic vector potential. So in the dipole case, when you write it out, magnetic field can be written as a function of the magnitude of the dipole moment for the magnet you're looking at the field of, and the distance from that magnet to the point where you're calculating that field. And so along the magnet's axis, this simplifies to this value right here. And so the magnetic energy of one dipole sitting in the field generated by another is given by this formulation, which is basically the volume integral of the magnetization in some space, which happens to be, in the case of the point dipole, just the magnitude of that magnetic dipole. And then when you take the dot product of it with beta, showing that it's at a maximum when they're aligned, you get this formulation here. And if you compare that to a couple of slides ago when we just calculated the integral of force or torque, you see that this approach gives you 1/2 of that previous value. And that's because you're only calculating it for one magnet in the field of the other, not vice versa. So you have to multiply it by 2 in order to get the energy of the full system. So we've shown that it's equal to the analytical approach, but since the coil field equation is slightly different, it requires another validation or two. Next slide. So now we get more complexities. And so there's two methods for calculating the magnetic field from a circular coil in space. The first one is the Biot-Savart law, which basically says that you discretize coil 1 and you calculate the field at a certain point in space, say here. You calculate the contributions from each element around this coil at that point. And then you can get the sum total of the magnetic field and the direction at that point in space. And so that requires integration, and that's not really numerically efficient. So the coil vector potential approach, you can write the magnetic field as a function of the complete elliptic integrals, which are sort of known integrals that for a given argument you can quickly calculate the results. And so you don't have to have that full integration and loop over all of the individual segments. And so it's a little, all things considered, I verified that both methods equal each other, and this one is faster. So I use this one for the rest of the work. And so both methods require at least one summation to get the forces and torques, because yeah, you're getting the field at this point, but you also have to get the field at each point around this coil and then get the forces and torques as a result of that. And so again, you can only really compare these to the previous results in the far field when they're at least 10 coil radii apart. And the near field, we expect there's going to be some pretty interesting differences between our previous results and our new results. Next slide. So I mentioned that the vector potential formulation is a little bit different when you're looking at coils versus dipoles. So in this case, you can phrase the magnetic energy of coils as a function of inductances and currents. It's one way to do it. You have your self-inductance related terms on the outside here, and then a mutual inductance term because of the flux linkage between the two in the center. And so you can calculate each of these terms. It's great if you already know the inductance, but in this case, we don't. We need to calculate it somehow. And so you can calculate each of these terms in terms of the vector potential in a similar way. In this case, you're taking the volume integral of the current density around that space. And it's a little different because now you have it curling, through space rather than a single point. And so you have to have the vector potential direction and magnitude at each point. Interestingly, the vector potential is always azimuthal to coil 1 in the case of the circular coil. So it's strongest when it's right there centered around where the moment of the coil is, and it decreases in magnitude as you go off in any direction in any axis. And so we validate these terms two ways. We compare the self-energy terms with the self-inductances against Jackson's estimates for self-inductance energy to show that they get the same thing. And we validate the mutual inductance energy terms against Grover's published inductance tables. And so we can show that we're actually getting the correct results for magnetic energy in that way. Next slide. So I mentioned we were going to get some interesting results compared to the dipole case. So on the left-hand side here, we have the 1 degree freedom rotation case where coil 2 is allowed to rotate. And we have, again, beta along the x-axis and the non-dimensional torque along the y-axis. And in this case, we're plotting it for each of increasing pi over kr star, so 0.1, 10, and 100. And so we can see that they all have equilibria at the origin as expected, and that one of the curves, the intermediate curve, has these two secondary equilibria. So if we look at those potential energy curves, we see that as expected, the one with the weaker magnet is statically stable at the origin because it's not strong enough to overcome the restorative spring torque. And in the intermediary case, we actually see a statically stable equilibrium at the origin and two unstable secondary equilibria, which is not what we saw in the dipole model. And the reason for this is that if you have just points in space, you can calculate your forces and torques just based off the distance between them. As soon as you start having coils with dimensions, as one of them, their faces a certain distance apart, as one of them starts to rotate, part of the coil is getting closer to part of the other coil. And so you actually have effects that come from the proximity of those coils that dominates the other, like the broader trends of the system. So in the case of this system, whereas in the previous case the magnetic torque caused it to diverge and rotate until the spring torque overtook it, in this case the magnetic force between the two parts of the coil that are closest actually is restorative until you rotate a certain amount. Once you reach a certain rotation amount, this actually creates a divergent magnetic torque rather than a restorative one, and you end up having an unstable equilibrium where you have that crossing. And so in the 2 degree of freedom case, and I need to take a second to explain this plot to you because you'll see it or something similar to it several times. We have beta along the x-axis here, we have distance along the y-axis, and each point on this plot, green, red, or black, represents an equilibrium in either for red, force, green, torque, or black where they overlap, a mutual equilibrium. So that's, the red dots are where force balances and equals 0 in x and beta, and the green dots are where the torque balances. So in the case of torque, you can see that beta equals 0. On one side, you're going to have a negative torque, and on the other side, you're going to have positive torque, so you have a crossing there. And so where they both cross or are black is where you have both a force and torque balance. So you actually have equilibrium in your system. And so you can see that we have a equilibrium where beta equals 0 that's roughly analogous to the 1 degree of freedom translation system, because beta equals 0, and you're basically looking at how far the force forces you apart on that axis. And then as you rotate off to either side, you get these secondary equilibria as they get closer together. And if you look at the potential energy contours for this system, you see that it's very similar to the 1 degree of freedom rotation, in that you have that statically stable central equilibrium with 2 statically unstable equilibria on either side because of those proximity effects. And you see further proximity effects down here. So you're thinking, why do we have all these red dots that are kind of crazy down here? And so at this distance apart, at roughly 0.5 distance, you actually start to have overlap of the coils. So you have your coil here, and this one actually crosses across there. So whereas this force was initially pushing these apart when they were crossed, now this force is causing forces like that, which is causing a torque in that direction. So you're actually seeing it go from a positive force trying to push it away to a force where they're actually trying to pull them together in that region. And so that you get a crossing between positive and negative there. Next slide. So now I'm going to talk about the real-world applications I mentioned, which are those that are sort of more similar to an actual spacecraft design, and then go through the conclusions, my contributions, and vectors for future work. Next slide. So the real-world problems are those that more closely resemble an actual spacecraft design in some way than what we've done up until now. I mentioned those methodology goals earlier. I've selected sort of 3 ways to show how these goals have been met. One of them has already sort of been shown to you throughout the presentation, and that's non-dimensionalization of the model, so that you have your visualization is easier and more intuitive, and you reduce the variable space and make it a lot easier for someone to see how changing one variable could affect the stability conditions. Scalability we show by adding a coil to the system. So we've been using 2 coils so far. What happens when we have a 3rd coil? And so that shows sort of, we can look at some of the trends that persist between 2 coils and 3 coils and see how they change. And then plausibility we do by seeing how changing assumptions affects the stability conditions that we've got. So for instance, we've used springs up until now, which are capable of compressive force when they're close enough together. But when you're actually stowing something in a launch vehicle, you're not going to want to be compressing springs and trying to stuff them in there, unless you're doing strained energy deployment of some sort. You're likely going to want tethers that you can coil up that aren't capable of exerting those compressive forces. And so we explore how using tethers instead of springs changes stability. Next slide. So we're going to jump right in with the 3-coil system, where we have, again, coil 1 fixed at the origin. Coils 2 and 3 are positioned, again, linked with linear springs. And they have distances between them, x2 between 1 and 2, and x3 between 2 and 3. And so coils 2 and 3 are allowed to translate along x, but not allowed to rotate. And each of them, you can see that the current in each coil is such that they repel the adjacent coils to them, so that the system is expanding and repelling itself. We have 3 plots here that represent for increasing chi, so stronger magnet or weaker spring, for the same radius coil. So for the case where all the coils are have a coil radius of 1. And then down here we have it for when we have different radii. So we go from 1 to 1.2 to 1.5 radius. And so in this case, we see the distance in x3 along the x-axis and x2 along the y-axis. The red circles represent equilibria, force equilibria for coil 2. So that's where coil 2's forces sum to 0. And coil 2's forces include both of these springs, as well as the magnetic effects of coils 1 and 3. So you see that the coil 2 equilibria actually run along the line x2 equals x3. Because the system is symmetric, coil 2 is only in equilibrium when it's equidistant from coils 1 and 3. So that conceptually makes sense. We see that as chi grows, you have an equilibrium sort of near the natural length of the springs here, and it increases in both x2 and x3 up to like 3 points something there. And that makes sense. You have stronger magnets, the springs are going to stretch more. These green equilibria are force equilibria for coil 3. And coil 3 does not quite see the same symmetry as coil 2. And so what you see is that as x2 goes to 0, this line of green equilibria curves back to the natural length of the spring. So at x2 equals 0, coils 1 and 2 are basically on top of each other. And because their currents run in opposite directions, their magnetic forces on coil 3 cancel. So there's no magnetic forces, there's nothing to result in the spring being stretched. And so that conceptually makes sense as well. For the different radius coil, we don't see that cancellation at x2 equals 0 because coils 1 and 2 are of different radius. And we also see that the equilibrium move farther out in both x2 and x3, and that's because the coils are bigger, so they're stronger. And so that tends to make sense. Next slide. So this is the 3-coil system where coils 2 and 3 are allowed to rotate around Z. So they're fixed at a distance of 3 from each other, and that sort of prevents that crossing effect. And their torques are resisted by a torsional spring on each coil. And so we go from, this is a potential energy plot with angle beta 3 on the x-axis, beta 2 on the y-axis. And red represents, again, coil 2 equilibria, except in torque this time, green is coil 3. And we have increasing chi over k star. So 1, 2, 3, 4, 5, and 10. So your magnets are getting stronger as you go to the right and on the bottom. And so what we see here is that for very weak magnets, a slight rotation in one coil means that the equilibrium for the second coil rotates slightly as well. And that makes sense because they're otherwise all at equilibrium at beta equals 0. Which we established previously. But also, coil 2 is the only one that has its current going the opposite direction. So coils 1 and 3 are generating magnetic fields that are basically summing together in the same direction. And so coil 2 wants to rotate to be in the same orientation as coils 1 and 3. And it sees sort of a double whammy effect of both of them trying to induce that rotation. So in all of these plots, coil 2, you see coil 2's equilibria changing quicker. Because it really sees twice the level of torque, roughly twice. Whereas coil 3, it's already aligned with coil 1, but coil 2 wants it to rotate, but it's farther from coil 1, but it's already in the same direction, so it really catches up later. So you see that as when chi equals 2, you go from you have the statically stable equilibrium at the origin, and that's where your spring torque is still dominating, but if you rotate enough, because the magnetic torque is at a maximum when they're perpendicular to the field, you actually have an unstable equilibrium here on either side where the magnet starts to dominate. And then right near beta 2 equals plus or minus pi over 2, you actually see the spring start to dominate again. So you have stable equilibria at the outside here. So that's kind of cool. And then as you continue to increase, for instance, in chi equals 3, you see that it takes a smaller rotation for the magnetic torque to dominate because the magnet's stronger. And then you see a switch of stability of that central equilibrium from statically stable at 3 to statically unstable at 4 and continuing on. And then once the chi equals 10, the magnet always dominates the spring torque for both coils. So you can see that there's sort of, there's definitely a space where you want to be in it depending on whether you want the coils to be parallel or not. So it's not simply a case of stronger magnet or weaker magnet is better. There's some interesting trees you can do here. Next slide. So now we move on to replacing springs with tethers. So whereas before we had a spring along here that basically stretched or exerted elastic force just as the distance between the coils changed. It did not change with angle. Now we have two tethers that are attached sort of at the equal points when they're parallel to each spring, and they change directions as they rotate. So as coil 2 rotates, you end up with a tether that looks something like that. So they're no longer just parallel to the x-axis. And because they each have a spring constant of k star, they're kind of giving almost double the force of the single linear spring. So we expect that the equilibria occur a little bit closer to the natural length of the spring in this case. Then when we look at torque, now torque is also dependent on distance apart. And it changes a little bit because whereas before you had, on one side it exerted a positive torque and the other it exerted negative, and it's always linear, a linear function of beta. This gives the comparison of the tether and spring torques. Here's beta, here's your torque. This straight line is that linear relationship for the spring. With the tethers, you see that between roughly beta equals plus or minus 0.75, it actually overestimates the magnitude of the torque, or not estimates, but it overshoots. And as it approaches beta equals pi over 2 on either side, it underestimates the spring torque. So we expect to see some interesting differences in force and torque equilibria between the spring and tether case. And so in this case, we have the springs on this side and the tether on this side in the 2-degree of freedom case, going for a chi over k star equals 0.1 to 1 to 10. And you've seen a couple of these plots before. On this case, it's the same chi over k star, but with tethers. And so quickly you can see that whereas the force equilibria the elastic forces did not change with angle before, so it was just this slight change in magnetic force from the rotation of the coil. So you didn't really see much rotational dependence for a weak spring. You see a very, very drastic change in the force equilibria because now at distances below 2.5, if 2.5 is the natural length, you don't have a positive spring torque that is supplementing the positive magnetic torque. Now you actually, if you rotate enough, you actually have a negative force because the coil is rotated enough and it's stretching and it's pulling it back in the x direction. So you definitely see some very interesting changes in the force equilibria. The second thing you see is that whereas for the weak torques, you only really saw the torque equilibria at the origin and then a couple due to the proximity effect closer to 0, x equals 0, now you actually see secondary equilibria forming. And remember, these green equilibria show up anytime torque equals 0. So the reason that they're showing up for even weak magnets is because of the difference in this plot. So in that middle, closer to 0, you're having a very, a much stronger tether torque or elastic torque than you have the spring, and that's very weak on the edges. So it actually is able to be dominated by the relatively weak magnetic torque in this case. So you see that the appearance of that sort of V-shaped feature much earlier or for much smaller chi. And so it also gives you some very interesting potential energy well shapes. So you're seeing some triangular effects. And so if you really wanted to get down in there and say, okay, I'm going to be seeing this kind of torque over the course of my life cycle, how can we change the shape of that well and maybe give it a greater potential energy in this direction? You can definitely play with the elastic hardware to find that. So next slide. So now I'm going to give sort of a recap of the contributions. I focused on the primary one in this talk, which is the development of that general stability analysis methodology validated for nonlinear magnetoelastic space structures. I identified conditions under which they're stable. I've located specific passively stable geometries, which if you'll recall satisfies that second question, which is do any of these even exist? I have defined equilibrium conditions as well as static and dynamic stability conditions. I've described how changing the assumptions in the elastic hardware shifts the stable geometries and compare them, and also just the creation of the model for the forces and torques in the system. The secondary contribution, which I haven't focused on as much in this talk, but is sort of the topic of chapter 2 in my thesis, is identifying and exploring a number of space applications that could benefit from an electromagnetic subsystem, or be enabled potentially. And so through that, I enumerated the capabilities of electromagnets on such spacecraft. I conducted system trades to quantify those benefits. I identified key enabling technologies that would make this technology possible, as well as feasibility risks in doing so. Specifically reduce the risk associated with system instability, which is a big one. Something I got asked about so many times at conferences is what happens, aren't magnets unstable? And then I developed a technology maturation pathway of key applications that would get flight heritage and basically advance the TRL maturity of the technology. Next slide. So in conclusion, stable configurations of these electromagnetically supported structures do exist, and they depend largely on the ratio of magnet strength to spring stiffness and the degrees of freedom. And this sort of answers a question that we encountered early in the work, in that there are not so much regions of stability in the configuration space as there are individually statically stable points with a region of permissible bounded motion around them. And that's a very important distinction. And then there's also a clear trade between stability, as you've seen that the statically stable points are dynamically stable for weaker magnets in general, and stiffness. So you get greater stiffness with stronger magnets, but your stability decreases. So there's clearly a trade there, which is another really cool thing to see. So there's so many different ways you could take this in future work. I don't even know where to start because they're actually really cool. You can expand to higher dimension shapes than just a linear structure. You can start making triangles and spaces in more than one dimension. You can study more degrees of freedom. You can take a specific mission profile requirements, such as we're going to see this much magnetic torque from the Earth's magnetic field, and basically backtrack it to what you would need stability-wise out of a configuration. Studying the effect of, instead of using constant currents, changing currents in the coils, so that as they move apart, eddy currents may be induced, and it may reduce or increase the total current in each coil. See how that affects stability of the potential energy curve. Fill in that configuration space. Actually explore a lot of different combinations and angles as you get to these higher dimensions shapes with machine learning approaches such as support vector machines. And the potential for exploiting metastability. So you actually have, in some cases, more than one statically stable point. What if you added directed energy in that direction such that it actually switched between stable configurations? That was a really cool thing that Professor Lorenzini pointed out that I think is a really neat thing you can try and do with these structures. Next slide. So with that, I'll open for questions, and special thanks to my committee and everybody who made my graduate career possible.
Okay, so we'll open the floor for questions.
So can you discuss a little more of the scalability?
Okay.
So you went to chapter 6, which had 3 coils, 2 of which were moving.
Mm-hmm.
Can you sort of take us beyond that and say what are the challenges that?
Okay. So one of the challenges with having, let's say you add a 4th or 5th coil or something like that, is that in this case we're not studying other degrees of freedom that include lateral motion potentially. So maybe if you had some sort of gravity gradient that occurred at these longer scales, you might have that as sort of a persistent added source of energy. So there are potential things that arise with more coils and greater lengths of structure. Is that what you were getting at?
Part of it. Look, when I think about scalability, I'm thinking in 2 dimensions, and maybe I'm not thinking, but let me try this. That there are more degrees of freedom. So just even with your simple case of one fixed coil and a movable coil, you could add rotation in the other direction, you could add shear and all those things. And then there's more degrees of freedom, and then there's more coils around which you have to do these integrals, right?
So you're thinking of scalability maybe the numerical methods?
Sure.
Okay.
Well, are those 2 different things? Are those 2 different things, more degrees of freedom versus more coils around which you need to,
I think so. I think
integrate, because you got to do all the pairwise combinations, I guess.
Yeah, so in terms of adding degrees of freedom, you definitely sort of introduce potentially the shear forces and torques that would require different tether configurations to, you know, provide resistive elastic force in that direction. And in the case of expanding the model to more coils, one of the things that you could do is you could potentially modularize it, that you have sets of 2 coils, and you could calculate the general field around a set of 2 coils at a certain distance, and then basically sum them up. So you could do some cool things where you're actually adding numerically the fields together. And there's a lot of things you could do with lookup tables and basically calculating the magnetic field and then just multiplying it by chi. And that's actually what I did in a lot of my methods is I calculated just the basic dimensionality of the force vector.
Is there some point where, let's say you have a whole bunch of coils, where you can start ignoring this pairwise combination because all these others dominate? Is there like a criteria by which
you could decide to cut off after, like, once your contribution to the total, you know, magnetic field at this point is less than 5% or something, you could potentially ignore it.
Is there some, well, so you picked a small percentage, 5%,
Yeah.
but that may depend on what your dynamic stability
Yes.
energy is.
So yeah, there would be a linkage between the critical initial kinetic
So rather than
energy.
just picking a small number.
Yes. And there's also a dependence on the external torque you're seeing. If you're seeing a constant torque from the Earth's magnetic field of a certain value, you don't want to be cutting off magnetic fields that are close to that value, for instance. So I think it's going to depend on your system assumptions as well.
Can you think of a criteria by which you would use to
cut off the magnetic field.
cut off? I'm thinking back to my days many decades ago in model reduction.
Yeah.
Thinking about if I'm willing to tolerate a certain amount of truncation error, then I should cut off at this
Well,
point.
so you could do that. You could say that if you have a critical kinetic energy of like 0.005, what that represents is that some rotation or some change in distance that results in that addition of energy. If you could backtrack that out and find out what the difference between maybe the field at that point, and the field of, the field at the statically stable and the field on the statically unstable point, and you could maybe say, no, we're not going to decrease things on that order because it's too sensitive. I think you could basically have a sensitivity analysis that tells you what magnitude is
Where you
important.
can cut off certain couplings.
The same direction of a question that Dave asked. I'm thinking of a system which is very simple, like two coils. But of course, I think, as you pointed at the beginning, the importance of this analysis is also towards building large structures.
Mm-hmm.
And so my question is a little bit technological. If you look at how large can it be by using superconducting coils and what sort of the order of magnitude that could be reached?
So you're asking like how long
Yeah, how
to
long?
make these things?
Not by just adding many coils, but really, maybe it's the case that you presented at the very beginning. You have a big mirror, you have a secondary mirror, you will have two coils. How far can I go?
So
With present technology.
if you're considering that they're attached elastically and not free-flying the formation.
Attached elastic.
Yeah. So with the superconductors, so how do I phrase this? I assumed maybe 80 amps through one of the